Welcome back. We'll continue on with another couple examples of related rates problems. We've got, for this problem, a 10-meter long ladder resting against a wall, and then the bottom of the ladder is sliding away from the wall, and the top of the ladder is going to wind up sliding down. So we have this relationship between the top of the ladder, the bottom of the ladder, and how they are moving. So I guess maybe a little diagram would be useful here. So here's my little wall, my ground, and then I guess here's my ladder. My ladder is 10 meters long, so that little distance there will always be 10. I'll have x will be how far away the bottom of the ladder is from the wall, and I'll have y being how far the bottom of the ladder is, or the top of the ladder is from the ground. So I have those 2 points, the bottom of the ladder and the top of the ladder. And it says the bottom of the ladder is sliding away from the wall. So this point is moving to the right. So in other words, dx dt, my horizontal position is changing at an increasing rate of 2 meters per second. So if it had been instead somebody was pushing the bottom of the ladder towards the wall, then dx dt would be negative. We'd be moving in a leftward direction. Similarly, if we're thinking about dy dt, if the ladder is going to be sliding down the wall, then I would expect dy dt to be negative because the direction is heading downwards. If my ladder was sliding up the wall somehow, then dy dt would be positive because y would be increasing. So already in the back of my mind, I'm expecting a negative value for dy dt. I know that as the bottom of the ladder is sliding further to the right, if I'm increasing in the x direction, then the top of my ladder should be sliding downward. I should be decreasing in the y direction. So dy dt, I'm predicting it to be negative. So we have dx dt is 2 meters per second. We want to know how fast does the top of the ladder slide down the wall. So the question is, what is dy dt? And it says when the bottom of the ladder is 6 meters away from the wall. Okay. So I guess the first thing would be a little assumption that I can make is my wall is meeting the ground at a 90-degree angle. So if that's the case, then I have Pythagorean theorem that I can invoke. I can say that x and y and 10 are related by the Pythagorean theorem. X squared plus y squared equals 10 squared. Or in other words, x squared plus y squared is 100. And easy enough for me to differentiate both sides with respect to t. So derivative of x squared is 2x times dx dt. Derivative of y is 2y times dy dt. And derivative of 100, that's a constant, its derivative is 0. I'm just going to put a little star by this because I don't quite have everything I need. So if you're looking for what we're looking for to solve, it's what is dy dt. When we've got a value for dx dt, we have a value for x, but we also need a value for y. So I'm actually going to need to do a little bit of side work first before I can find out what dy dt is. I need to figure out when x is 6, what is y? So as a little side question, so if the value of x is 6, what's the value for y? Well, we had our equation that x squared plus y squared was equal to 100. And of course, x is 6, so x squared is 36. And that gives me y squared being 64. And of course, technically you could say that there's two potential values, positive and negative root of 64. Of course, y is the position of the ladder, and of course the ladder is not underground, the ladder is above the ground, so a y value being negative would not make sense here. So I'm going to take only the positive square root and say that y should be positive 8. So we've got our x value, we've got our y value, and now we're good to go. So using our derivative, putting in everything that we had our x value was 6, the value of dx dt, that was 2. We had y is 8, and dy dt, that is the thing that we're solving for. And now all I need to do is clean things up. 2 times 6 times 2, that's 24, and 2 times 8, that's 16. And dy dt is negative 24 over 16, which turns out to be negative 1.5, negative 1.5. So as expected, the change in the y value is negative because our ladder is sliding down the wall. It's heading in a downward direction. So the ladder is sliding down the wall. At a rate of 1.5. And then this is where we need to go back and remind ourselves, how were things being measured? Specifically, distance was being measured in meters and time was being measured in seconds. So that negative 1.5 is also being measured in meters per second. So my ladder is sliding down the wall at a rate of 1.5 meters per second. I don't have to say negative because the sliding down implies the negative, the fact that my distance is my direction is a negative direction because I'm heading in a downward direction. Okay, so we've got this problem involving the London Eye. It's a big Ferris wheel that they've got on the shore of London. And the radius is about 60 meters, so this is actually fairly accurate to real life. If it's working properly, then the London Eye does one revolution in 30 minutes. So if you're sitting in the London Eye, you'll go round twice in 1 hour. So the idea here is that we're going to get in at the bottom of the wheel and we're going to travel around slowly in a counterclockwise direction. And the question that we're interested in is, how is our horizontal position relative to the center of the wheel? So in other words, how is our left and right sort of motion changing when we've done 1/8 of a full revolution? So first thing, I'm going to do some little drawings down below. First thing that I would say here is, number one, if we're thinking about this, it's a circle, and I'm imagining the center of the London Eye as being the origin. And if you're imagining starting off at the bottom and doing 1/8 of a full revolution, so a quarter of a revolution is 90 degrees, so an eighth of a revolution is 45 degrees. So when we're talking about having done a 1/8 of a full revolution, you got in at the bottom and you traveled counterclockwise 45 degrees. In other words, if we're thinking in terms of where are you in angle terms, you're at the angle of 7 pi over 4. That's where you would be. When you get into the carriage at the very bottom, you're at 3 pi over 2. And after you've traveled 1/8 of a revolution, you're now at, angle-wise, 7 pi over 4. That's the first thing. Some other things that we've got going on here is that the wheel is doing one full revolution every 30 minutes. So we could say stuff about how the angle is changing, because again, we're interested in doing a certain percentage of a revolution. In other words, we're talking about angles, so it might be nice to know how is that angle changing with respect to time. So I know that I'm doing 2 full circles every hour. That means in 30 minutes, you will do 2 pi, and another 30 minutes, you'll do another 2 pi. So the angle is changing 4 pi radians every hour. Okay. All right. So let's continue on. We've got some of our beginning stuff thought of, but we need to now come up with what is our equation? How are we going to deal with things? So this is where we need something that involves x, because if we're thinking about where we are in the circle, there's an x coordinate that's involved and a y coordinate. We also need to think about it being related to our angle theta. And so this is where maybe this is a little trickier one because it's not as obvious where the equation is going to come from. But I give it here in the hint. If you're a circle centered at the origin, then any point on that circle, any x and y point, the x coordinate is just r cos theta and the y coordinate is r sine theta. So actually we have an equation involving x's and angles. X is just r cos theta, and we know what r is, the radius of our London Eye, that's 60 meters. So x is 60 cosine theta. Okay, and now away we go. We can get into figuring out what is the change in x, and let's do that. Let's differentiate both sides with respect to t. And so we've got the derivative of x with respect to t, that's dx dt. Derivative of cosine, that's negative sine. And the derivative of theta, that's d theta dt. And now let's go and do our first part of the problem. The first part was asking us at what rate is our horizontal position changing? So how is the x value changing when we've done 1/8 of a full revolution? So in other words, for 1/8 of a revolution, we have, at that point, the angle is 7 pi over 4. And d theta dt, that was 4 pi. That was how fast our angle is changing with respect to time. So now we're pretty much ready to go here. We just have to do a little bit of calculating. Sine of 7 pi over 4 is negative root 2 over 2. So you'll have negative of negative root 2 over 2, which is the same thing as positive root 2 over 2. And as I calculate this out, that turns out to be 120 root 2 times pi. This is about 533.1459 and so on. Of course, we have to talk about units, and this is where we need to go back. When we were creating our equation for x being r cos theta, our radius was being measured in meters. So in other words, that means our x values and our y values are being measured in meters as well. So that means that this dx dt is in terms of meters per hour. And of course, I don't want meters per hour, I want it kilometers per hour. And so that's an easy enough little change to make. 533 meters is 0.533 kilometers. So therefore, dx dt is about 0.5331 kilometers per hour. So that means as you're doing 1/8 of a revolution, we're traveling at a speed of just about half a kilometer per hour in a rightward direction, which makes sense because if we're thinking back to our picture, as we're traveling around this circle in a counterclockwise direction, if you're at that position, having done a 1/8 of a revolution, you're still heading in a rightward direction. So dx dt is positive. We are heading further to the right as that happens. The second question was asking us, and there's another one, how is the rate changing when we're at the top of the London Eye? So the other part, when we're at the top of the London Eye, that would be up here where our angle is pi over 2. So let's do the second part of the question. So if we're at the top of the eye, that's where our angle is pi over 2. So we'll have 60 times negative sine of pi over 2 times 4 pi. Sine of pi over 2 is 1, so we have 60 times negative 1 times 4 pi, which is the same thing as negative 240 pi, which is the same thing as 753 and a little bit negative, sorry, 753.98223. So in terms of kilometers per hour, because again, this is in meters per hour. So in terms of kilometers per hour, our x rate of change is about negative 0.75398, or rounded off to 4 decimal places, 0.7340. And of course, this speed is a speed where the velocity is leftward direction. We're traveling to the left at a speed of 3/4 of a kilometer per hour, which again makes sense if you're traveling around this circle, and by the time you get to the top of the London Eye, your little carriage is now heading to the left. It's no longer heading to the right. It was heading to the right until you got to the far right, then it's heading to the left. So my speed at the very top of this London Eye is 0.75-ish kilometers per hour, heading in a leftward direction.